initiated at the request of the National Stone, Sand, and Gravel Association. So several of their members are online here, but also several people from outside as well. It's not intended as a specific address to them. It is a general presentation. It's going to be recorded. And, yeah. Thank you.
If by chance have a spare set, or that's okay.
Is that better?
Yes.
Excellent.
Okay.
Thank you. Okay, this discussion was initiated at the request of the National Stone, Sand, and Gravel Association, but it is not intended as a specific address to them. It's going to be recorded. We're going to begin recording here shortly, and I would ask that people hold questions until the end so that we can do that more effectively. And I don't intend to record your questions and answers because this is going to go on the Chicago District's YouTube channel. So just the presentation will be posted on that after it's recorded. But I guess we'll go ahead and begin. Okay, we are now recording. Have you muted them? Okay. We're going to mute all the speakers and then we'll take questions at the end. So just to give a little introduction to myself, I am the district geologist for the Chicago District of the Corps of Engineers. I've been in the district here since about 2001. Before that, I was in the private sector, and I've also worked for the St. Louis District of the Corps of Engineers for about 14 years, from 1980 the mid-90s. So been around the upper Midwest and the Midwest especially, and banged around quarries and jobs that use large stone, and as well as tunneling and blasting and a number of other geological disciplines. The Corps of Engineers is broken up into divisions that are individually broken up into districts, and each district has some autonomy with respect to how they handle stone, sand, and gravel procedures, contracts, and purchases. This map shows the geographical distribution of the districts and the headquarters of the various Corps offices, district offices, and division offices. The geographical location of them has some relevance with respect to natural material sources, as some areas have distinctly different geology and different access to stone, sand, and gravel materials. The upper Midwest includes Chicago, Detroit, and in the adjacent district division, we have St. Paul District and Rock Island District. This map shows a lot of the Chicago and Buffalo District projects. If we were to zoom in, or if you zoom in on the slides when you download them or whatever, you'll see all these are harbor projects along the Great Lakes that the Corps of Engineers has a hand in, as well as other projects on rivers and drainages within our districts. And many of them use stone, sand, and gravel products. We're going to focus on armor stone because it's a unique product that we use for erosion protection and wave protection in the Great Lakes, as well as in the districts that have coastal projects in the Atlantic and Pacific Ocean environment, and the Gulf of Mexico as well. Armor stone acceptance is not pre-approval. That's one of the things that I want to start out with, is that probably every year of my career, I have fielded calls from suppliers that say, what do I have to do to get on the approved list of stone suppliers for the Corps of Engineers. And the simple fact of the matter is, most districts do not have pre-approved lists of stone suppliers. They have lists of suppliers that they know have a history of being able to provide stone and gravel and sand products for our projects. But most contracts require an approval specific to that project or that contract because the demands or the needs of projects are unique in some respects. And so there's no one size fits all set of specific criteria for every district or every division in the Corps of Engineers that we have as a universal situation. Armor stone is defined in the Corps of Engineers engineering manuals for coastal projects and erosion protection. And there are basically three designations. Armor stone, A stone is the outer layer or outer unit that consists of the largest stones. Interior to that is B stone, which is gradational to prevent the core stone, the C stone, from migrating out into the water bodies or to basically stabilize the structure. And C stone is the finer core material that is gradational between B stone and the foundation material. Oftentimes we will put down, if we're building from scratch, we'll put a geotextile mat to filter foundation material to keep it from washing into the core material and subsequently out through the voids in the larger stone, the outside the projects. A stone, B stone, and C stone are not absolute size designations, they're relative size designations, and they're specific to each project. And many times we'll run into situations where a stone size that is a B stone on one side, on one project, would be big enough to be an A stone for another project. So A stone, B stone, and C stone refer to the relative positions of these materials in a structure. Again, A stone is the outermost armor protection. It's the largest stone in the structure, and size and gradation is designed based on Hudson's equation and ice conditions in northern climates, because ice can be an impact on structural stability as well. And the durability is critical because that's the stone where it's facing, that's the stone facing the most severe environmental stresses. And the general assumption is that quarries that produce good quality A stone can readily produce B stone or C stone, but the reverse is not always the case because the largest stone has to be free of discontinuities or weak zones that can break down the stone into smaller size in response to environmental stresses. There's kind of an involved equation for that, for the size of A stone. It's based upon these parameters, and I won't go through this equation, but it will be in the it'll be in the quiz at the end. Yeah, that's a good idea. I'll put it in the quiz at the end. No, there's no quiz. B stone is placed as a transition between C stone and the outer layer of armor stone. And gradation is designed using filter compatibility concepts to prevent the C stone from washing through the large voids in the A stone layer. And some B stone sources produce small quantities of larger A stone as a consequence of their production processes, but they don't produce a lot of it. Sometimes but they'll set aside, if they have out of size stone, they'll set it aside and eventually accumulate a large enough stockpile to actually compete market-wise for based on jobs of, appropriate size demands, quantity demands that they've got stockpiled for. C stone is the core stone. It's the base of the structure against the foundation, and it's often riprap sized or slightly larger, not subjected to direct wave action or major current impacts. And it's, like I said, transitional between foundation materials and overlying B stone. Durability is important, but not as critical in the outer layers of stone because it's not subjected to the same stresses. And C stone sizes are equivalent sometimes to larger grab stones. Sizes used by state highway contractors or state highway specs are often used to make it easier on suppliers that are used to producing larger quantities of stone for highway department contractors. So that, they don't have to reinvent the wheel as far as their grizzly settings or their eyeballing gradations in the quarry. Other materials that are related to these, riprap is more commonly used in non-coastal projects, non-coastal districts along riverways or smaller lake shores where wind may cause waves that erode shorelines. Fillstone is oftentimes not as strictly regulated or not as strictly specified in terms of gradation. It has a broader tolerances for stone size gradations. Ecosystem stone for habitat. Typically, we use oftentimes rounded stone for creation of man-made ecosystem enhancements where we make riffles in streams or provide aesthetic features for in adjacent areas. And then there's concrete, aggregate, sand, and clay fill that are sometimes byproducts of quarry operations or primary products depending on the deposits. Stone shape is important in terms of armor stone use. We want stone to be relatively angular so it interlocks tightly, or the interlocking of the slope of the stone slopes are stable. And for that reason, we go to something with an aspect ratio of 3:1, which is basic 3 parts of the longest axis can be no greater than 3 times the shortest axis. And those axes are generally the longest dimension and the shortest dimension of the stone. Ecosystem stone for habitat, again, typically rounded with specific dimensions to create habitat for streams. Doesn't have the same stability criteria, doesn't have a lot of the same criteria as armor stone. Sometimes we try to reach a happy medium between the two, but for armor stone, we oftentimes have very relatively steep slopes, sometimes up to 2:1 or so. And that's simply not possible to have a stable slope using rounded stones. Stone contract types are important to consider. Excuse me. We have general construction contracts where armor stone may be part of an overall contract for construction of a shoreline feature or a shoreline revetment or breakwater, but there may be other elements of the contract. Construction contracts can either involve a lot of different things or can be specific to use of armor stone. But those construction contracts include furnishing, transporting, and placing the stone. And those contracts are written up as a construction contract as opposed to the next type of contract. Stone supply contracts are written so that we can purchase armor stone that the Corps of Engineers internal maintenance crews will use to repair or maintain structures within our districts with our own equipment and manpower. And so those are just basically stone supply contracts, like we're buying a raw tonnage amount and we'll have it delivered to either a stockpile location, a stone dock along the lakes, or delivered to a project where our crews are actively placing it on a structure. And those contracts are somewhat different in terms of how they're administered, but they are similar or identical in criteria for stone quality. And the gradations are determined based upon the same hydraulic parameters by the hydraulics engineers. This gives a geologic map of Wisconsin, which kind of shows the hows and whys. We have stone in the Chicago district and Detroit district and even parts of the eastern St. Paul district the way we do. We have a number of different stone types in Wisconsin that are different than in the central Midwest. We have the southern half of Wisconsin is largely sedimentary rock. Then you get into areas around Wausau where we have granite. And up in the northern part of Wisconsin, we get into what geologists refer to as the greenstone belt, which is some of the very oldest rock on Earth. Some of it's over 1 billion years old. And there are very dense, very hard crystalline rock in those areas. So we have a wealth of different geologic materials available to us from a resource standpoint in the upper Midwest. And it just depends upon how they are developed by quarry and resource providers as to how good that works out. We have several types of armor stone we use. These are examples of dolomite, massive, thick, very thick beds of Silurian dolomite in the upper Midwest, in the carbonate deposits. These are, this is from Hayton Quarry, I believe, in about 20 miles west of Manitowoc, Wisconsin. We have different rock types available, like I said, but we still have to have rock types that are free of discontinuities or planes of weakness or weathered features. We prefer, if we're using dolomite, to have it massive with thicknesses at or larger than the minimum dimensions of armor stone, because those bedding planes are going to be planes of weaknesses along which the stone will break, either during blasting or excavation, or during placement or transportation, or over time in the structure. Crystalline, or what is colloquially called hard rock, granite, quartzite, andesite, or metavolcanic rock, are rock types in Wisconsin that we've used that are of Precambrian age. They include, like I said, granite, quartzite, and the metavolcanic rock in the greenstone belt. Some sandstones may be used for armor stone if they're extremely durable and don't have a lot of weakness planes, and some what are called oolitic limestones, typically referred to as Indiana limestone, because they're predominantly quarried in southern Indiana and are used for things like doorstep architectural stone, because they're easily carved and have a somewhat gritty surface texture that's safe to walk on even when it's somewhat wet. But that stone tends to be softer, but it still can be fairly durable in environments where abrasion is not as much a concern. Again, this is a massive quartzite. This is a quarry outside of Waterloo, Wisconsin, where gray quartzite is mined, and massive granite deposits around the town of Wausau, Wisconsin, also used for armor stone. Control there. Whoops, something happened here. Some stone is in addition to being blasted, is cut to size for armor stone. Large cable saws or mechanical saws are used to cut stones that are beyond the 3-to-1 aspect ratio tolerance, or are just simply too large, and were quarried in such a way that you have less blasting impacts, less cracking, less fracturing, and so forth, and they cut them to size that's a time-consuming process, and the equipment is not as readily available as drill and blast equipment. And I don't know if that's what, it's just a video, I don't know if it's showing. But,
Oh, yeah,
there it
yeah.
is. It's like a giant chainsaw, except it's, operated on the end of a tractor. And then there's also methods of quarrying stone that don't have as severe an impact as blasting, using drilling and wedging, where they actually drill holes close together and then drive wedges in it to split the rock in that fashion. And you can sometimes get a very straight line breakage with that, depending on the rock type. There's also occasionally reused armor stone. Some of our projects have existing armor stone that we reuse as part of the project if we're doing modifications to it or maintenance of it. And that can be basically a recycling activity. These stones were ballast stones used in fishing vessels from all over the world, that fishing vessels that come to Iceland to fish for cod, and they unload their ballast stone and fill their holes, fill their storage areas with fish, and take them back to fish markets wherever they came from. And, so Iceland has actually accumulated armor stones from all over the world and use them on their shoreline. Stone is tested in labs for a number of different physical parameters that we use. Laboratory tests used to determine the durability of stone we require comes from Corps of Engineers validated laboratories. We have a couple of labs ourselves, but we also permit stone to be tested for our use. It's tested in private laboratories, but the labs have to be validated by our materials testing center. And there's a list online at this website of laboratories that have been validated by those folks. The website has a listing of laboratories nationwide, listed by state, so you can search by state and find out what laboratories are available in your area that have been validated. For decades, the Corps of Engineers had laboratories all over the country in its own districts, as well as using private labs. And there were, one time in 1980, there were over 200 labs in the Corps of Engineers itself that did testing all over the country on soil and rock for projects when we were building lots of dams and levees and coastal projects. Then as the 1980s went on, fewer and fewer large government contracts and projects were being built. So that, and there was also a program under the Office of Management and Budget called A76, which was, in which it was a reflection of political beliefs that the government shouldn't be doing all this testing and that we should turn a lot of that over to the private sector. So the Corps' number of labs shrunk, and a lot of this work was then turned over to private laboratories, and the numbers diminished accordingly. The Corps of Engineers, up until very late 90s, had a research center in Vicksburg, Mississippi called the Waterways Experiment Station. And they had the oversight authority of certifying laboratories both within the Corps and validating laboratories in the private sector. They also were responsible for cataloging all the data from these laboratories on materials used in Corps of Engineers projects, whether it was clay, sand, all the way up to armor stone, concrete aggregate, erosion protection, and fill stone. They had massive collections of data every year, and that was compiled by an office down there in Vicksburg, Mississippi. The There is no current agency-wide database identifying sources for Earth materials. There used to be a system of cataloging that based out of our Waterways Experiment Station, but in the late 90s, they closed the Waterways Experiment Station, and it was reborn into something called the Engineering Research and Development Center, which had a different laboratory function that was, instead of having an annual overhead budget to operate, was operated on a project by project basis and was funded entirely by project funds. So it became less consistent in terms of its manpower, and also a lot of the functionality of the original laboratories fell through the cracks. There are no current agency-wide conventions for the approval process, although the Great Lakes districts have a general consensus as to how we do things. And each division might have that within itself, within the division. That's really controlled somewhat autonomously. The contrast would be a pre-approval versus case-by-case, project-by-project approval. And in the Chicago district and in some of the Great Lakes districts as well, the general procedure is that materials are approved on a project-by-project basis because individual project needs vary. Those specifications will include the test requirements, the acceptance criteria, and a process by which we conduct source inspections, and also may include by policy updates to material inspections and testing if necessary. There's an evolving problem within the agency and within agencies in the government that build large projects. There's a fluctuation in technical expertise within the different levels of our bureaucracy, and we've relied upon intermittently input from the private sector, labs, AEs, and universities, and we also have developed centers of expertise within the Corps of Engineers. Institutional knowledge and expertise was lost in the 90s as Waterways Experiment Station closed and many of our division laboratories closed, and we downsized as an agency in terms of the technician and laboratory testing, and senior people were retiring and not being replaced with personnel at the same functional level. So we had a brain drain, if you will, as well as a technology drain at the testing level. This is a hard slide to read, but the Waterways Experiment Station used to compile published concrete aggregate and riprap data in expandable loose leaf binders by geographical region that had every test recorded for Corps of Engineers projects nationwide. And by the 1980s, it was broken up into 6 volumes by geographical region, and then expanded into 16 volumes. By 1994, there was an effort to adjust to the digital age and consolidate that information into CD-ROMs. But then in 1998, the database was supposed to go online and be managed by Waterways Experiment Station, but in 1999, Waterways Experiment Station disappeared. These are the old blue books that some of us still kept as souvenirs, almost, just as kind of a reference to where sources might still be if we were looking to figure out what sources might be available. And the binders were such that every year the Waterways Experiment Station would send updated test information for each source that they tested. They're, again, drawn out by the 16 volumes by geographical region, and they included aspects of transportation, local knowledge, and similar geology. The reports within them contained a map showing the location of the project, location of the source, and what types of materials and what the test results were for those materials. And in the late 90s, the combination of the application of A76, which reduced the in-house services of drilling, laboratories, and surveys, along with what was called the BRAC program, the Base Relocation and Consolidation Program, that reduced the numbers of divisions and districts in the Corps of Engineers, and also the number of military bases. And it cut down a lot on the institutional knowledge within the agency. And the result was kind of a rough transition. There was an effort in the late 90s to deal with this. Engineering Regulation 111.0-1-205 says that every district is supposed to furnish its test results to Waterways Experiment Station in Vicksburg, Mississippi, but that didn't exist. So and there was no funding to execute that regulation. So it is an unfunded mandate to an entity that doesn't exist. So an impossible thing to happen. Again, this data was supposed to include all the quality controlled laboratory testing and identify the source data with respect to its location and size, production and points of contacts. Basically, everything that we used to do was supposed to be carried on, but it hasn't. The data from each district was supposed to be sent to Waterways Experiment Station within 30 days. And that has never happened because Waterways Experiment Station doesn't exist. So again, to summarize it, we had the capability in-house to do testing, to catalog that testing, and to track it through a central center of expertise and distribute it to all the entities that needed it. We lost that. And again, we went from a number of district and project funded laboratories to an almost ad hoc arrangement. But all that's kind of history background. Again, this is leading up to in the late 1990s until 2001, because the Great Lakes had a lot of shoreline erosion projects in response to fluctuating lake levels and storm damage in urban areas. And a number of different types of contracts were being initiated by the districts around the Great Lakes, Chicago, Detroit, and Buffalo, and stakeholder agencies like the urban areas along the lake fronts. A committee was formed to develop standardized specifications and to establish a network among the professionals dealing with these types of issues. And we met quarterly to both discuss issues related to projects and also in an effort to standardize our processes. And the result was that we produced a Great Lakes Armor Stone guide specification that was used as a general template for shoreline erosion protection and revetment designs in the Great Lakes. But even before the online databases, there was still within the Corps usually a designated person in each district who handled information for materials like armor stone, gravel, and riprap. And these were kind of the go-to guys that were sought out for information by designers if they needed information on what materials were available and where and when. And as the agency aged, a lot of redundancy disappeared, and different districts became one person deep in this expertise. When that person retired, those sorts of things fell through the cracks. The changes in in general federal policies with respect to meetings among specialties and reduced overhead budgets and budgets for things like conferences and training affected the information exchange within the agency. And so there became fewer and fewer of us old timers that knew how things were, what sorts of things were out there to be used with respect to things like sand, gravel, resources, and stone. So we have an increased demand for rapid information distribution because our contracts are now issued very quickly and designs are being done faster with digital resources and technology. We have reduced funding for non-project billable lab tests or for overhead use. We have reduced funding for non-project billable labor. And we have more limited opportunities for information exchange meetings. So, there's no longer a one-stop source of material information like there was when we had Waterways Experiment Station with the materials experts down there and their catalogs of data on material resources testing. But that's the history of how we got to where we are. And some of the people I'm sure on here are interested in what we do as far as quality control and what our criteria are for armor stone. This is an example of stone that has been inspected at a quarry by a quality control staff person. It's designated with X's on three sides at least to indicate what the issues are with respect to its quality that have rendered it unacceptable. The X indicating unacceptability. The nomenclature on the side here indicates that there is an aspect ratio issue. This stone is clearly outside of the 3-to-1 aspect ratio, and it also has been marked with red paint along this fracture that indicates a break in continuity of or a fracture that renders it unacceptable. So inspection for large armor stone is applied to virtually every stone. It's examined with respect to its whether it is within the gradation required, and within the general size, and within the aspect ratio. Cracks from blasting and excavation and handling are examined, and if they're significant, they're marked or the stone is rejected. Bedding planes that are planes of weaknesses are examined, and if they're significant enough to reject the stone, it's not used. Vugs, which are voids in the rock that form during lithification, when the rock is formed, if they are aligned and in a layer, can form a plane of weakness along which the stone can break. And stylolites are a type of discontinuity within stone that, if they are not fully mineralized, can be a plane of weakness and can provide a pathway along which water can seep and cause freezing and thawing fracture, as well as wetting and drying fracture. Weathered zones where you have horizons within a stone that has clay minerals that are susceptible to moisture and expansion are causes for rejection. Mineralized areas with mica or weak minerals or clay minerals and weathered chert in an armor stone that can cause stone to fracture are also things that are not acceptable. The inspection of processing and inspection of processing and equipment can be is also done during inspection of the source to see how the stone is moved, how it's moved from the face once it's excavated, and how it's loaded and transported and conveyed to either the site or the purchase point, if you will. If material is handled roughly, even big stone will break. Also, the reviews of the specifications and processes with the suppliers and the operators is a means of quality control for the products. Vugs, again, are discontinuities within the stone mass, and chert is a mineral type that or a rock type that is prone to taking on moisture and causing stone to fracture either armor stone, riprap, or concrete aggregate. And stylolites are these sutured discontinuities within rock that can be planes of weaknesses and cause it to break. Laboratory test data that's used for determining whether armor stone is appropriate or acceptable include determinations of specific gravity, absorption. The Los Angeles abrasion test is a test in which stone pieces are mechanically turned in a drum with ball bearings or like steel balls, mill balls, to see what kind of durability is exhibited in rotations. And freeze thaw tests, where you take a slab of rock that's been cut, and freeze it, thaw it. And wetting and drying is basically the same thing as freeze thawing, except instead of freezing and thawing it, you're wetting and drying it. And then we have a standard practice for field examination in which we determine whether or not there are deleterious or unacceptable materials contained in the rock mass. We expect generally that laboratory results must be representative of the stone type or the rock type furnished, and must be at least 5 years or younger from the date that the testing was done to the contract date, and must be done from a USACE validated laboratory. Criteria for these that are cited in this table are generalized for our use in the Chicago District shoreline projects, and they may be adjusted to different project needs. Clearly, if you're working in Galveston District or Puerto Rico or Fort Worth District or Jacksonville District in Florida, you're not going to need to worry about freeze thaw. And so some of these numbers are adjusted also for that, and also for some of these areas like Mobile District or Jacksonville District might not have the highly durable rock materials that we have in Chicago area for use, so they might have to lower their standards just because of the availability of material. The service records that we require for our analysis of a project are records of basically the materials track record. Has it been used recently in other projects that are similar? Similar in scope? Has the source had to provide material of the same quality and quantity as the project that we're trying to build? We have some specific restrictions in the Chicago district. We have projects in the lower parts of the Great Lakes in the Indiana shore, along the Indiana and Southern Illinois coast, where the wave heights and the frequency of storms and the height and the potential for ice damage are such that we restrict the use of stone to the most durable stone types, generally non-sedimentary stone types. And their advantages to that are twofold. One is that it's more durable in the project environment. The other is that it's more durable during handling and processing, and because it is more durable and massive, it's less critical that the adherence upon QC inspection is lessened, and consequently it gives us greater peace of mind in terms of the durability of the material in the long term. The quality control for armor stone, it also involves major considerations of cost, market factors, and supply and demand. Transportation costs are extremely significant to earth material sources, because you're talking about large volumes of material, often transported great distances. So fuel cost is a relevant cost concern. and order size accordingly. Less important costs considerations might include stone type and the season in which we require the material. Most suppliers have some stockpile on hand, but there may be difficulties with that depending upon circumstances like COVID or even seasonal workforces and that sort of thing, and can't quarry stone as under as great a control in areas in the upper Midwest because stone behaves differently when it's blasted in frost zone areas versus non-frozen ground areas. The costs for armor stone have varied quite a bit over time since I've come to the Chicago district. When I was here in 2001, armor stone was in the range of $35 to $40 a ton. It's gone up significantly, and most recently, it's in some places it's gone up over $150 a ton because of cost of considerations, maybe of workforce, maybe of transportation costs, or even equipment costs because much of the equipment was difficult to find parts for during COVID. All the other post-COVID price chaos situation we've encountered that really nobody has found a magic equation for yet. The quality assurance for armor stone is what we do as the Corps of Engineers. We perform quality assurance in-house on stone sources, and it's based on 3 evaluations: laboratory test results, performance records, project records, and quarry inspections done by a geologist. You can't make bad rock into good rock. You can't glue it back together, but you can make good rock into bad rock through bad practices in excavating methods, poor handling, and poor placement methods. Lab results can be biased by sample size and detection and selection, because if you pick the absolute best piece of rock and take the absolute best part of that best piece and test it, it's going to perform incredibly well. If you take a lousy piece of rock out of a good pile of rock and test the bad rock, you're going to get bad results. So there is an inherent risk of bias, and the research that we've tried to do over the years has tried to give us a better handle on whether certain tests performed on stone sample sizes that are 5 pounds or less are relevant to a piece of stone that is 25 tons. You know, how representative can it be? We use them as guidelines, but we recognize that they can't be applied on a one-for-one basis. There's also a good potential that sources may not have much performance record. There are new sources or sources that have gotten into the market for armor stone that may not have provided a lot of armor stone in the past. So you have to rely upon assumptions that if the stone has good lab results, and if the quarry looks like it's well run, and if the stone that is produced so far looks like it would perform well, that has to weigh heavily in lieu of, or in the absence of, good performance records from past projects. Quarry inspections have to be done by experienced geologists, and we provide insights into the quality of rock, suitability, extraction methods, and so forth, and the competence of the operation of the staff that's involved in processing and transporting, placing the stone. The source evaluation approval or rejection is hopefully done in a timely, objective, and consistent manner with within the specifications. We have strived to eliminate any biases based on, human factor. And we recognize that the staff and the equipment of quarries varies over time. If a quarry produced poor quality stone 20 years ago and they've made improvements in staff, equipment, and processes, that has to be taken into consideration. These processes include reviews of laboratory test results, comparing them to specifications, review of work plans, quality control plans, and the contractor with respect to the provisions and specifications. This is a kind of a warning slide that I put together for a presentation, you know. We cut our abilities to inventory material sources available to us for core projects in the late 20th century, just about the time when things started hitting the fan. The 1993 Mississippi River flood caused massive damages across the Midwest. Hurricane Katrina came along in the early 2000s, and Superstorm Sandy came along. This slide was made 3 years ago. Who's next? Sacramento. Gee, what's happened in California in the last 6 months? All these enormous storms that have hit the West Coast have caused enormous flooding and stresses to structures in California. St. Louis District has massive, long strings of levees along the Mississippi River. Jacksonville has a series of dikes around water bodies in Florida. Memphis is along the Mississippi River, close to the New Madrid earthquake zone. Nashville has had lots of flooding. So we've got climate change with aging infrastructure, and we will have needs for armor stone and riprap and large quantities of earth materials to repair, maintain, and improve infrastructure in this country. And we, as an agency and as a federal government in general, we need to better understand where these materials are and what the quantities are and what the quality of the material is and how quickly it can be transported to areas where it's needed. In the near term, we've oftentimes relied upon state highway agency specifications and lists of sources, but there are advantages and disadvantages. Obviously, the state highway departments have large databases and they have a lot of track record of them, the materials being used for aggregates. But the minuses is their gradations are smaller than ours, and they're dependent upon use in highway projects, not hydro projects or coastal projects. The testing protocols may be different than the ones we use, and the project life for highways and bridges is different than the project lives for dams. We have dams in our inventory that are over 100 years old, and I don't think there's a highway in the United States that's had a pavement that lasts 100 years old. And so the places that we need material are at the mercy of other, and this places us at the mercy of other agencies, highway departments, quality controls, and they can change their specifications, and they're under no obligation to tell us what their what changes they make and what the basis of those is. It requires communication among agencies to do that, and highway department budgets and our budgets are independent of each other, so we don't have that that comedy of functionality. They have large databases, and we use them a lot. We have some long-term and midterm expectations. We have I've been putting this engineering regulation on the docket every time that we've met as a community of practice among geologists and geotech engineers nationwide. It's out of date and it needs to be revised. We also have a rough plan for a core-wide web-based materials database GIS system that would link test results and material sizes and types to a point-and-click type map where you could point on a location, say, I want to know who has this size material within 100 miles of the site, and that sort of thing. We need to coordinate with industry. We need to maintain communication with industry. And we need to be more consistent across the agency nationwide and within the regions so that there isn't confusion or conflict among districts as to what is and isn't acceptable material. And this that pretty much is my wrap up. At this time, I think what we can do is cut off the recording and we'll go to a question and answer session. If anybody has any questions, what I can do is I'll try to respond now. If I can't, I will ask you to send me an email. I'm happy to respond to an email. And like I said, this recording will be posted eventually on our district's public webpage, a link to our YouTube channel. And it can be, reviewed, or you can pass it on to folks that weren't able to attend. The intent is to get this information out there and to communicate with the industry as best we can. And thank you for your attention. And I think we'll shut off the recording and open it up for discussion and questions.